Okay, hi everybody. So here's a Marantz Model 1180 DC, and it was featured in a previous video where I went through the process of field testing a piece of vintage audio gear. Kind of some things you can do with minimal test equipment and in short amount of time, when you're out, at a flea market or a yard sale or something, you want to test one of these things out. I went over that. So check that video out if you get a chance. And from that video, we learned that there is most likely a shorted component or a faulty component in the main amplifier on one of the channels. The other channel possibly could be okay. And the way we determined that was by measuring right at the speaker protect relay, which is back down here, and found that there was a negative voltage on one of what would be connected to the speaker leads if this relay pulled in. So kind of working back from that, we got that determination. So what I'm going to do in this video is I'm going to pull this amp module out and just go through it and randomly check the components. Well, I'm not going to randomly do it. I'm going to do it in a method, using a method. Okay, so this just comes right out of the amp. It's really easy to remove. This is one of the most service-friendly amplifiers out there. It's really nice to work on, at least so far. Anyway, the heatsink and the power amp board and everything all come out in one piece. And my wife just came down here and informed me that today is my birthday. I forget about it every year, so I guess happy birthday to me, whatever. Anyway, opening this up, you can see they have these diodes on the back of the board, and they use this thermal, or not thermal, they just use this glue to hold them down. Really gross. And you can see that they start to get, like this one, see how it's getting all disgusting. So these will need to be cleaned and replaced and so forth. And that glue will eat. This is the type of glue that's corrosive to the traces and so forth. So we'll need to clean that all off. So let's see, here to here. And I have a voltage drop in that direction. And you can see that's not a dead short, so we're probably reading across a resistor. Okay, so let's look here. Same thing. All right, and if I reverse polarity on my meter, same thing. Okay, so there's other components in here. That's the point that I'm making. So we're not going to we're just looking for shorts right now. That's all I really care about. Same thing here. Okay. That is a dead short. And that noise is so annoying. I hate, that's the only thing I don't like about these meters is and you can shut that off, the sound, but you got to hold buttons and go into menus and stuff. But anyhow, this thing's shorted all the way around. So there's a bad one. That's a bad one. And it kind of reads, there you go, that one's, so this one's shorted from, looks like collector to base. Let's look at this one. So it'll go from collector to base, dead short, collector to base, dead short. So these are shorted now. It doesn't mean that they're all 100% shorted because these are in parallel. You might have some other components connecting them together. So we know this side's bad, this side's probably good. Okay, the driver transistors are on these heat sinks. So and this is a pretty unique circuit, especially with the bias, and we'll go over that a little bit later. So that's not a short, that's another component. So that's good. At least we don't have any dead shorts. Okay, so those are good on that side. And then let's look at this side. That's shorted. So we have a shorted transistor there. Okay, so that one's shorted. So we do have a shorted driver as well. So we see there's a charred resistor, and there's one that has just collateral damage from this one burning up. So we have bad components over here. If we look at this diode right next to the resistor, it might be good. It is. And this one, it is. Looking at our current mirror, and this might be PNPs, I don't know. That one's good. That one's good. And then here to here. And there's the base. There and there. Okay, so those are somewhat okay. They're going to need to be replaced anyway. Go back to resistance. Here's another resistor that looks to be cooked. And I don't know what value it should be. It's a low value. You can see it's probably a 10 ohm. It's open. This one here is 10 ohms. Open. Ah, that was my mother calling to wish me a happy birthday. My day is complete. She's 92 years old. She was one of the early people in, computers. Worked with the old IBM System 33s, and definitely one of the heroes of my life. So it looks like we really have our work cut out for us here. You can see all the corrosive degrading glue down here. You could see we have a component down here that's really, I don't even know what it is. It looks like it used to be a diode at some point. Bottom line is this board is going to have to be gutted and cleaned properly, and then repopulated with good components. Now, things like resistors and so forth, I'm going to leave alone. Caps are going to get replaced, and I'm pretty much going to do a wholesale replacement of transistors. The input pair on this, they use JFETs. It's a JFET input circuit. We'll look at the schematic in a little bit. And they're these inline JFET packs. Hopefully they're good. I'll test them. If not, I have some JFET packs like this. I just don't know if they're the correct pinout and the correct type, but I know I have these of some form. Hopefully I won't need to use them. Okay, here's another one. Got 2 resistors for the price of 1 now on that one. So yeah, lots of work. Okay, here's the transistors out of the other channel. These are the PNPs. Oh, that one's good. 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 And we're just doing a quick spot check on these right now. Good. 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 Now this is the NPN, so we can switch the leads. So these are all good as I suspected. So these will probably go up on the curve tracer and get kind of checked out a little better eventually. And if they're still really good, I will keep these as spares to use for repairs. All right, so I have a little update here. I got the back of the board cleaned up pretty well. Got these all remounted and re-insulated and cleaned. I tested every one of these thermistors and these bias diodes. They're all good. So put them back in. Going through this, and you can see there's a lot of burned components over here, and I'm slowly going and cleaning this up. And I'm replacing all the transistors. And I got to, let me see, where is it? Right here, Q716. And, well, there was only half of a Q716. So that had to be replaced. And this is the current mirror, and they are both thermally coupled. You can see they made them with this little heat shrink thing, and they put some thermal glue in between, if you can kind of see that in there. So looking at the one pair on the bad side, you can see one of the transistors has actually failed. Sometimes if you do it, it'll say that there's a short. So Yeah, there's a lot of bad transistors on that side. Two of the drivers are bad. That Q719, one of the current mirrors, and we'll look at the circuit design here later. So I'm just going through, and so since those are matched for the current mirror, I'm using my little homemade curve tracer, and we have it turned on. And if I go up here, you can see that's transistor number 1. And there's transistor number 2. And they are perfectly matched. All right, time for a little update here. It has been days and days and hours and hours and hours of work. This thing is the recapper's dream. I have never seen so many capacitors on one of these things before. And I don't know what it is. There must have been a coupon sale on 3.3 microfarad capacitors, because there is a gazillion of them on here. So I was able to clean up the main power amp board pretty good. The only thing I didn't have was these 22K potentiometers. Yes, they're 22K. And it's hard to find 22K pots. DigiKey does have them in a single turn version. The multi-turn are gone the way of the dodo bird. You can't get them. They're just sold out everywhere. So that's not going to happen. These ones seem to be working just fine after cleaning them. So I'm inclined to just leave them in there for now and not mess with it. There were a ton of bad resistors, and you can see I still have one left because these 24 ohm resistors are kind of oddball values, and I have some 24 ohm, but I don't have them in this wattage. All the ones I have are half watt. But there were many, many bad resistors on this board. There were a whole bunch of bad transistors. There was a whole bunch of, there was actually several diodes that were leaky. Really catastrophic failure on one of the channels. A lot of the capacitors, like these film ones that were those green colored ones, they were dried out and the cases were starting to crack. Although when I tested them, they were good. But I wasn't about to leave them. But just to give you an idea, look how many caps was in this thing. It's crazy. And so I had the drivers and the bias transistors on one side were bad. Many open resistors, many out of tolerance resistors. I went through every single resistor and had to test them. That's a rarity. Normally you don't have to do that on these. I redressed these thermal tracking thermistors, and I used an actual thermal glue to fasten them to the heat sinks here so they can track better. And you can see on the front where they had these thermistors and diodes mounted, like marked on the front, but they are mounted to the rear of the board. And they had that glue, which is horrible stuff. And what I use is this stuff. I use Chip Quick electronic grade silicone, and I also use that other stuff, and I think I showed you that before. If I have one handy here, I'll show it to you. Yeah, right here. And it's electronics grade silicone. Either one of these will be good. You just want to use the stuff that's not going to be corrosive to the board like that glue was. New capacitor filter caps, and got rid of the bad ones that were in there. Although when I tested them, they tested okay. Even though that one had that big leaky spot in it. I don't know where it rolled off to, but here's one of them. And the bad one is right here. You see how bad it was. So those are replaced, and you can see them in here. I had to modify this little ground plate. Had to cut some off with the cutoff wheel because the lead spacing is narrower on the new capacitors. And you're all going to ask me what model cap I used, aren't you? These are 63 volt, 22,000 microfarad, and they are Chemet. You can see. And I don't know what it says here. 23, 34, 233-22079 is what these are. Okay, so we're all together now. And I did this all in one take. And what I mean by that is I recapped the whole thing, rebuilt this whole amplifier board, replaced the transistors, the capacitors, all the bad resistors, did all the testing, everything, cleaned all the controls, you name it. I did the whole thing without ever turning this on and trying it. So this is the first time I'm going to plug this in since I put it on the bench. So let's undo the cord here, and I'm going to go over here. You should be able to see the bulb from where you are. And let's go for broke. How about that? Okay, so the safety relay still has not come in. And that's over on this side. So now we're going to have to do some voltage chasing and see where we are. There is a possibility that I put something in wrong because, again, I tested all my work as best I could. I don't think anything, there's a backwards capacitor or anything because that bulb went very dim, if you noticed. So that's not drawing excessive current. So something's just not happy. So now I'm going to just connect permanently to ground here so I don't have to keep holding this ground probe somewhere. Okay, and just make sure that we're good. Yep. All right, so let's look up here and see if we have any. And no, so far, well, there's our 30 some volts there. I'll have to look at what one that is. It might be that it's supposed to have that. Okay, so we're on JN13. So let me look that up on the schematic. Okay, not good news because looking at JN13 right here, where are we? JN13, that leads directly to a speaker lead. So JN13 is going to one of our power amp channels. So if you follow JN13, which is this pin right here, it goes, let's see, 13. It goes up, across, comes down here, and it appears to go to this channel down here. Okay, so I was just getting ready to troubleshoot this thing, and I remembered something. So I pulled the module back out here because it's only a couple plugs and 3 screws. Can you tell what the problem is? I mentioned it earlier here in the video and then promptly forgot to deal with it. It's this resistor here. You see? That's the problem. And if you look at the schematic, those resistors are the actual emitter resistors for your driver transistors. So there's one here and one here. And they're 24 ohms at a half a watt. So there they are, 24 ohm resistors. And that's an odd value, the 24 ohm. I have, in stock, I have 27 ohms and I have 22 ohms. And you would think those couple of ohms don't really make a difference. But you have to understand, transistors are current-driven devices. And if you look at this VBE drop here, they're showing there's only about 0.6 of a volt, or 600 millivolts right there. And that's between here and here. Changing this by a few ohms will change the operating point of this transistor, because when you play with the VBE current, that current is amplified, because that's what a transistor does, by the beta of the transistor. So if you change the current by a little bit in here, you change it by a lot up here. So if the gain, for instance, if the gain at DC is like 100, for instance, whatever change you make in current here will be multiplied 100 times here. So that's why they chose that odd value. And you could play around with these numbers and maybe change some things and it would work. But really, I want to keep it the way they designed it, okay? Whoever designed this knew what they were doing. It is properly designed. I ordered a set of 24 ohm resistors. And by the way, Mouser and DigiKey do not have them. They have some in lower wattage, but the bigger ones like this, because I really want to go with like a 1 watt, or the new half-watt resistors are very, very tiny, physically sized. That means that they can handle that much heat without burning up, but really they'll run really hot. So I want to go with like a 1 watt, and they don't exist. They're sold out, or not in stock. Okay, that is much better. So let's get this mounted in there, and let's try it out again. Okay, I am focused on the speaker protect relay. Let's turn the power on. And let's turn the amplifier on. And let's see if our bulb goes dim. It should. It did before. So let's turn that on. Okay, bulb is dim. It flashed. And we still don't have a speaker protect relay coming in. Well, that sucks. Okay, so let's see if we have voltage on our speaker terminals still. Okay, power on. And this was the one I think that had it here. I still have it. Jan 13. The other ones seem to be okay. It's still that same channel. JN13, that's what was giving us trouble in the first place. Okay, so let me look again. Okay, so I am now of the opinion that Marantz with this amplifier actually just outdid Sansui as the most flawed schematic I've ever worked on, hardly. This took a while to figure out. Now, I'm pretty sure all the components are correct that I replaced on the board. They are the correct components for the correct placement, because I did them one at a time. I only took one component out, put it, exchange it. I always do that so I don't get confused. But I had to go through and highlight this schematic and redraw it, in a way I could understand it, because a lot of these things are just not right. Like, for instance, on this channel is drawn correctly, but if you look here, they actually have the negative power rail. You can follow it all the way across if you want to, but this is the negative rail in purple, and it goes down into what they have drawn as NPN transistors, when in fact those should be the PNP transistors, and vice versa. Down here they have PNP transistors connected to the positive supply, whereas it's correct on this channel. In addition, this one is drawn incorrectly. It should be an NPN transistor, but they have it drawn as a PNP transistor. And of course, when you see that symbol and you're used to looking at it, with an NPN transistor, if it's not running in saturation, the base voltage is always going to be more or less positive than the collector voltage, and vice versa with PNP. So you're going through checking this stuff and you're saying, this isn't right. Well, it's because this symbol is incorrect. Now, I have the correct transistor in the board physically, where it's actually an NPN, but this will throw you off. If you're looking at the schematic and then checking a voltage and you're not thinking, that'll really throw you down a rabbit hole. So I had to kind of mark these what they're supposed to be, and then I kind of traced the signal path somewhat. So you can see where your class A signal path is here in the orange, and then it goes to your bias spreading circuit. And this is kind of a little bit different than a normal VBE multiplier or, you know, a diode bias spreader. But this is kind of where you're actually splitting the phase. So now you're going from your class A to your class AB over here, because this is now handling the positive or the negative half cycle, and this one's handling the positive half cycle. And so this is where you're going to start seeing your voltages, you know, change between the different devices. And I have almost the full positive voltage, you know, a couple volts of drop. I'm running this thing at half voltage right now, a little bit less than half. It's supposed to be about 50 volts on here. I'm in the 20 volt range just to limit current and so forth. It will work just fine on reduced voltage. It's just that your readings here will be different. But anyway, I'm getting positive voltage here at this point. And that's kind of where I am. So of course, putting a positive voltage here rather than, I mean, a big positive voltage. See, they're only supposed to be, you know, 100 millivolts on each one of these. This should be sitting at about 100 millivolts. And that's going to vary a little bit based on where you set your midpoint adjustment, you know, for your offset. And this is sitting at like almost the, you know, I have 20 volts in there. There's like 18 volts right here. So there's something wrong. So I need to go back and trace this. So now you're caught up to where I am. And I'll show you what I find here. Okay, as they say, show me where you've been and I'll show you where the problem is. So, as I was saying, I was getting a positive voltage on here, a real big positive voltage that we shouldn't be getting. And kind of chased my tail for a while. This is your positive line down here. And I came to this diode right here. And it just seemed that it's positive voltage up here, so it has to be coming from this section. So I'm looking for this Q754, and it was nowhere to be found on the top of the board. I looked all over the place. I looked on the, you know, the layout like this, and could not find it. So I flipped the board over, and lo and behold, here's these two diodes, one for each channel. And if you look on the schematic, it says pretty clearly that the cathode of Q754 attaches to the base of Q712. And of course, here's Q712 right up here. And if you look, I have the anode of the diode. I have this diode in backwards, and I replaced this diode. So that's me. That's a me thing. So that would be my problem. So I'm going to flip this around, and hopefully this thing should work now. So looking back at my picture, here's the original diode that was in there, all crusty and everything. And you can very clearly see the stripe, which would be the cathode on this top pin and the anode down here. And now that I have it flipped around, here, you can see it. It is correct. I just have to admit, I marvel at the individuals who, you know, other YouTubers who do this sort of hobby, how they go through and do all this stuff, and you know, it's like everything's organized and professional, and I wish I could do that, but this is the way it is when you're a hobbyist, I guess, and you don't do this for a living. And, well, and beyond that, when you're careless sometimes, as I can be at times, because I get in a hurry, you know, want to see it work, or I have something to do later on in the day, and then the next thing you know, I'm getting ahead of myself. And you don't check, even though you check your work, you can still make mistakes. And that's right there is living proof here, what I just did. Okay, I have it turned on. And previously, right here was a big voltage. And it should only be, you know, about 0.2 of a volt, because you can see they have 100 millivolts here and 110 millivolts here. That's how they want that. So you're going to see, you know, somewhere around that 200 millivolt range. And those two 10 ohm resistor junctions are inside this heat sink. They're kind of, I'm not going to move this too much because of all the clips, but it's right here for that. And yep, look at that. 290 millivolts on there. And if we compare it to the other channel that was working, exact same voltage. So now it seems to be working. Okay, I have this back in. Let me finish up these last couple of connectors here. All right, let's plug this in. All right, here we go. Let's turn this on. I'm going to flip this around so we can see the relay and see if it clicks. Okay, light flashed and went dim. Ah, it clicked. Did you hear it? Ha! I think we have success. It's pulled in. See? Okay, let's turn it back on again. Watch here. There it goes. Okay, with that in, we should be able to select speakers. And if I look on here, onto system 1, we'll go to millivolts. And system 1 is going to be this top one. Actually, I'll just look at it from the back here. 45 millivolts. Okay, let's get some clip leads on there and see if we can adjust it. Remember, the DC offset drifts all over the place based on your mains voltage. And so if your power supply voltage changes, which it did, because remember, we were only running this at plus and minus 30 volts, your DC offset will change a little bit. So let's get an adjuster here. Let's make sure I'm turning the right one. Yeah. Boy, look how touchy this is. This is with a 15-turn pot. Can you imagine trying to do this with that old single-turn pot that was in there? And what I'll do is, if this all looks good, we'll let it off the leash and go to full power. Okay, there's one channel. Here's the other channel. I'll adjust that. I think you can even see what I'm doing here, huh? So we should be in pretty good shape here. And again, there's no bias adjustment on this thing. Look at that. That is good, some good offset there. Okay, we're skipping ahead here because I didn't record a part here. That's another day, and so I'm coming back to it, and I missed a part. But to catch you up, what's happening now is the amp is working. But when I run this thing, you can see it's a beautiful looking waveform. But as I get up to clipping, see what's happening? Just before clipping, I'm getting an oscillation there. See how tiny that is? Now, when I first did this, the top and the bottom, you know, were oscillating pretty bad. And what it ended up being, as I'll show you, it was originally clipping, it was actually going into that parasitic oscillation, both at the top and the bottom of the waveform. And whenever it does that, that's typically, and it's symmetrical like that, it's typically going to be back in the voltage amplification, or the VAS stage, so back in here. And it's probably going to be, could be anywhere in this area. But the place that I traced it to was right here, where it was coming off of this DC balance circuit. Now originally I had moved this, changed this from a 1.1K to a 2.2. I thought originally that might have been my problem. So I went back to a 1.1K, so everything's exactly stock, and it still had it. It really didn't affect it at all. So what I did was I took a capacitor, just a little ceramic cap, and I shunted it right across this R723 here and R724 there. What that's going to do is, as that oscillation starts building up here on the feedback, it's going to shunt that to ground, because see, that cap is going to be right here. So I'll draw it in so you can kind of see what I mean. Like that. And I used a 270 picofarad, which at 100 kilohertz is somewhere around 6 kiloohms or 6,000 ohms. What I found was it almost completely eliminated it. But when you go to a 4 ohm load, it would still do it a little bit, you know. And you saw where we were. It was just a little tiny bit at the bottom. And at 4 ohms, there's still a wee little bit at the top and at the bottom. So the 270 picofarad isn't quite enough. I'm probably going to have to go up to a 330 or a 470 picofarad. Now this isn't, you don't want to go too far with it, because at some point in time it will begin to squelch out your feedback circuit, and you're going to get a weird looking frequency response curve. So the idea is to have it get rid of that oscillation at high frequencies, but don't get rid of the lower frequency feedback, because again, that's going to make your frequency response curve of the amplifier non-linear. So what I'm going to do is I'm going to take, and you can see the capacitors are right here. See if I can zoom in. Right here across these resistors. That's where they're at. So I'm just going to tack on a different pair of capacitors. I'm just going to go, like I said, I'm going to end up probably with either 330 or 470 picofarads, and that's going to just give you enough, hopefully, to get rid of all that oscillation. All back together, and I ended up relocating the capacitor to the back of the board, and putting it down with some of this silicone, which is good. And I did increase it to a 470 picofarad, although it made very little difference. It made it a little bit better, but there's still just a clipping. I mean, literally, as it starts to flat top at the bottom, negative half cycle, you start to see that just a tiny bit, but not enough that it's going to affect anything. And at the top half cycle, it's perfect. But here's the really cool thing. Doing the frequency analysis, so this is the first channel. Look how flat this amp is from 20 hertz to 20 kilohertz. And look how tiny the phase shift is on, from the whole frequency spectrum. That is, wow. So let me move over to the other channel. And I will need to switch these around, because we can only analyze one channel at a time. And I have my other test equipment on this channel too, so hopefully it won't affect it too much, but let's run the analysis. Hoping it will be just as flat as the other channel. I can't see why it wouldn't be. Look at that. Wow. Identical. So both channels have the same gain, and both channels are just as flat as one another. The phase shift is the same, so basically we have right and left channels are totally matched. Okay, the amp's all put together, and it doesn't look too bad. Okay, so we already know from our frequency analysis that the amplifier is very flat, and it does not invert the signal or shift the phase of the signal very much with respect to frequency, at least within the audible frequency range. So what we're going to do is we're just going to check 3 different points. We're going to check at 20 hertz, 1 kilohertz. We're actually going to look at 4 places. 1 kilohertz, 10 kilohertz, and 20 kilohertz. So those 4 points, and I just want to see what the distortion does. Now you have to understand, at 20 kilohertz and 20 hertz, the Keithley doesn't really work very well because of the filtering that's set in there and just the way this thing, it's at its limits for the THD measurement. So it's not going to give you a real accurate THD, and that's why we're going to use the waveform to check it at that. But once you get in that middle zone, you know, between a kilohertz and 10 kilohertz, this gets very, very accurate. All right, so we're going to start at 20 hertz. First thing we have to do is change this to chop. You have alternate and chop when you have two channels on an analog scope like this. And at lower frequencies, the waveform will be much more stable when you have it set to chop. And at higher frequencies, you want to set it to alternate, or if you set it to chop, it'll start being, you'll see little artifacts, and you'll see. I'll leave it like this as we go up, and then I'll show you what it does. Okay, so we want to slow this down a little bit, and I'm going to turn this up. And you can see how this shows, you know, a lot of distortion. It's really not that much distortion. And right there is where you're starting to flat top. And you can see that tiny little artifact there. And then it goes into clipping on both sides equally. So that's full power. Okay, that looks really good. So, you know, anything up into clipping, and you got to realize I'm at 20 volts per division right now. So there's, you know, about 25 volts right there, and about 25 volts there. So you do the math on the power. Okay, so now let's go up to 1 kilohertz. And if I turn this up, you can see I have to change my time base. And you can see already how you have, like, looks like these little squiggly lines following along there. That's because we're in chop mode. Now you can still read it, and you can see right there, you just get that tiny little artifact just before clipping. And there's about 75, 80 watts per channel right there. It clips like that at about 90. I was coming in at about 96 watts per channel, so it's way exceeding its 80 watts. Okay, and looking at the distortion, I mean, even near its main, you know, its max power, look at that, 0.025. That's really good. All right, let's go to 10 kilohertz. And now you're going to start seeing, you can see how that kind of gets funky looking. Now watch what happens if I go to alternate. See how clear that gets? So that's what those two settings are for. So again, look at our distortion. Beautiful. And as I go up, it really doesn't move until I get up to the clipping. There's clipping. Gorgeous. At 10 kilohertz. Okay, so I'll turn that down. Now let's go to 20 kilohertz. Okay, same thing. Beautiful waveform for 20 kilohertz. And you can see that the distortion meter doesn't even pick it up. Okay, and there you go. And you hardly have any artifacts at 20 kilohertz. And let's just do one more. We'll go to 50 kilohertz, which is more than we can hear, for sure. And you can see once again all the way up to clipping. It's beautiful. Okay, we're switched back over to the speaker sockets so we can listen to our speakers. And I have that turned into tuner because we want to check all the inputs as well to make sure they work. You always want to do that. A lot of times I will do that off camera, but you really want to do that. Okay, let me start this up. Oh, turn the speakers on, huh? Wow. Now I have the tone defeated. I don't have the loudness contour turned up at all. This has a loudness contour instead of just a loudness switch. So you can actually bring in and it has, what is it, 10 different steps of loudness contour you could add to it, which is really cool. This is an amazing sounding amp, and the stereo imagery on this is really, really good compared to a lot of the other ones of this era. This is a fabulous amplifier. Okay, so that works. Let's now switch over. We're going to move, turn this down. Let's move this over to the phono inputs. Let's start out with phono 1. And then in order to do that, we have to make sure we set this like that. So now I have the inverse RIAA curve put on there. And it would help if I started the song up again. Perfect. Okay, and let's move over to phono B. Make sure it works. Phono number 2. Okay. They all work. They all sound good. So, I am quite happy. So there's another project finished. Everything works, all the controls work. I'm quite happy with how it turned out. This one will be a hard one to let go because it sounds really good. I mean, it sounds good. That's all I can say. I'm really happy with that Rotel that I did a long time ago. It's still up in my living room. But I'll tell you what, when I listen to the stereo imagery of this and I listen to just how nice and clear the sound is, I'd say this one probably outdoes it. So whoever gets this is going to get a really nice piece of equipment. Okay, so that is it. That ends another series or another video here on this one. We're going to get it off the bench, and I have a lot of other things to do in the middle of all this work and everything else going on. That's why you haven't seen a lot of videos from me lately, because I just haven't had the time. So anyway, I hope you enjoyed this, and if you did, give me a like, whatever. It's the first time I've ever said that, isn't it? Doesn't matter. You don't have to do any of that. Just watch it and enjoy it. Until next time, as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again soon. Take care, everybody. Bye-bye.